Today it is our first virtual class for robotics. So, and from today we will start the second half of the semester, which is robotics. So before our lecture, I'd like to briefly review what we're going to do for the rest of the semester, which you may already see that from our announcement. So for robotics, we have 6 weeks left. And so in the first week, which is this week of robotics, we will talk about the basic concepts and keywords and everything of robotics. And from next week, and actually from the coming lecture, we're going to talk about the basis of robotics, which is the transformation and positioning and everything. And then we will talk about the forward and inverse kinematics, and followed by the velocity, forces, and Jacobian. So for the lab, and this week we will do the stepper and servo motor, and you have seen the pre-lab, and if you have no idea about how to do that, and I talk about it on the Friday before the spring break, so you may go to that HuskyCast and take a look. And also the pre-lab is still due tomorrow, which is Tuesday noon, and also in the following labs. And so our TA will post a video and showing how to do each lab, and on Tuesday evening. And we will post a video, so you will be able to see the video, and then you will need to answer questions or upload a video based on different weeks. And so if you have any questions, please feel free to email us, and we will try our best to answer your questions. And we understand it could be a hard time, but I want to emphasize a bit that everybody, please keep safe and also keep distance from others, and this will slow the transmission. And you know that a lot of nurses and doctors, they're facing a lot. So let's just save our medical system by lowering the transmission of the virus, the corona. Okay, so then let's start our lecture. And so I guess today is going to be fun, and we will have a introduction to robotics. Okay, so we have been talking about robotics for a long time. So what is the definition? So based on the RIA, which is Robot Institute of America, the definition of robot is that a robot is a reprogrammable multifunctional manipulator designed to move material, parts, or devices through variable programmed motions for the performance of a variety of tasks. What does it mean? It means a robot is, at least it has a manipulator. So what is that? That is the hardware. It can look like an arm or a person or a human, and so that is the manipulator. And also the key thing is the reprogrammability. So this is the key element in the robot that gives the robot its utility and adaptability. Actually, this is the key part to give its function, to give it function. Okay, and previously in this semester, we have been working with Arduino a lot. So, and also we have built our own controller. So for example, the PID controller, and you have written the code to control motors and stepper motors, servo motors. And so why we do that? It's because for robot is a combination of joints and links. So we do the programming, so we are preparing for programming the robot. And so in the real robot, and there could be a lot of motors. So for example, a lot means like 4 or 5 or even 6. And basically, and could be 3. Okay, and so what for programming those joints, and which are actually motors, and we could use Arduino to program it. And if we want to achieve further function, we want to achieve high function, and we need to use a computer. So for example, in the face recognition lab, which is week 10, we're going to use MATLAB to do the facial recognition. And so in a robot, if we want to have a robot that has very high function, so we need something that has more power. So I want to introduce a bit that in the industrial robot, what we use. Okay, so this is the page of ROS. So what is ROS? ROS is short for Robot Operating System. That is a set of software laboratories and tools. And so actually, once for all these type of manipulators and robots, you can install the ROS system in the computer. And then we will be able to program on this ROS platform instead of Arduino, and then this will further control the motion and everything. It has a very high function. And so but over class and as beginning, and we start with Arduino because it's easy to understand. And further, when you want to learn the next step of robot control and for example locomotion, and you may start with ROS. And there are a lot of materials, so you can read from their website, and they're starting tutorial and everything. Okay, so what are the advantages of a robot? So of course, and you may see a lot of robots in the market right now, and it can decrease the labor cost because it can replace some human effort. And also, it can increase the precision and the productivity. In the industry, there are already a lot of industrial robots that they have been working with human and as teamwork. And it increased the flexibility and comparing to the machines. And also, it can improve the human working conditions. So later, I'm going to show some examples of robots. So we will see that. Okay. So here comes the fun part. So I want to show some examples that I like a lot. And the first one is a video from another university.
This video presents autonomous control capabilities for a quadrotor helicopter.
So this video actually shows one type of robots that is the helicopter. So they can fly, and in here, right here in the center control, and it is able to program. And then once they have the different programming, and then they will be able to achieve different type of motions.
Okay, so we use a 20-camera Vicon system and an onboard IMU for state estimation. Here we show single, double, and triple flips. We developed a method for flying to any position in space with any reasonable velocity or pitching. We use the method to fly through windows at various angles. Here there's less than 3 inches of clearance on all sides of the quadrotor. We also fly between other quadrotors. The same method can be used to descend or ascend through a horizontal slot. By placing Velcro on the bottom of the quadrotor and on a target, the quadrotor can perch on a surface.
This is fun.
Here we demonstrate perching on an inclined surface.
So the control part is the key.
And now on an inverted surface.
Okay, so this video is from the University of Pennsylvania, and they have done a great job to control the quadrotor. And we
implemented an autonomous controller capable of recovering from extreme.
Okay. So for this example, and they have programmed the motion of the quadrotor in the controller and in the processor already, and so it can achieve a lot of different motions. And so next example is to control the robot joints to allow interaction with the environment, and this is also a very fun video. can see here is the sensor to monitor the human motion in real time. And this is the simulation tool. And these are wearable sensors to monitor human motion. Okay, so this is also a fun example. Okay, so let me stop it. Okay, so this is also a interesting example showing the robot and human teaming. So in this example, they use the wearable sensors to monitor the human's motion in real time so that it can interact with the environment and the robots. Okay. So the next example is also interesting, and in this example, I want to show that the robots that is designed in Northwestern University, they controlled applied forces to the robotic manipulator so that they can achieve the drawing and the control of the effector.
Aid. An honest likeness of drawing robot is doing a lot more than mechanical drawing robot is doing a lot more than mechanical engineers are working to fundamentally change how robots interact with humans. And the future looks very different from the now.
The classical view of what a robot is often this large robot that's very monolithic. It does the same task over and over, and it does it with a great deal of power at its disposal. And it
looks very different.
So here,
this is that's very monolithic.
So this is an example showing the industrial robots, and these are different robot manipulators and with different controllers, so they can achieve a lot of different type of activities and tasks.
Monolithic. It does the same task over and over, and it does it with a great deal of power at its disposal, and it does it with incredible precision and accuracy.
With support from the National Science Foundation, mechanical engineer Todd Murphy and a team at Northwestern University are helping a new generation of robots interface with the most unpredictable.
So you can see that here, right here, and they control the motion, and they also apply the forces right here so that they can both achieve the drawing pattern as well as the force. Okay, so that is also a very interesting example. So here I'm showing these examples to want to show that different type of tasks the robotics can achieve. And in our class, in the following few weeks, we will learn the forward and the inverse kinematics. So we will show how they really program the robots using the kinematics, also how they're going to control and how they're going to give different type of forces, Jacobian and velocity, so that they can carefully, accurately control the motion. Okay, so then let's start to talk about the real robotics. So before we start to talk about the manipulator and everything, so let's basically introduce some basic questions. So these are the basic concepts. So the first one is configurations. So what does configuration mean in robotics? So configurations refer to a specification of all points of a robot. So actually, when we talk about the robot motion control, what we're actually doing, we are actually controlling all the points. We name all the points with a coordinate. So it's like in the real world, in the robot workspace means in the robot world, all the points on the robot manipulator that we define it as a coordinates, that is a point. And the configurations, actually it refers to, we collect out the possibility of the coordinates of all these points. Okay, and for robot, and as I said, robot, it is a combination of links and joints. So although we see a lot of complicated robots, but actually when we really go to the details, and they're composed by a few joints, which are a few motors, as well as the links. The links are rigid bodies. Okay, and C-space. C-space, also called workspace of robots. So that is the space of all configurations. So it means that all the space that all these robotic points they can achieve. And the next concept is the degree of freedom. So that means the dimension of C-space means how many degree of freedom a robot can achieve. Okay, so then let's talk about these key concepts one by one. So the first one, which is the basic elements of robots, that is the joints. So we have talked about joints in our previous class, which is 3400, and we talk about different type of joints. And in robot manipulators, the common joints are revolute joint and prismatic joint. So this figure shows the drawing of the revolute joint, and this is 2D and this is 3D. And these two figures shows the prismatic joint, and this is 2D, and we can tell that we can see this type of prismatic joints a lot in different in different scenarios. And in 3D, and we use this type of drawing to represent a prismatic joint. Actually, in robotics, further in our robotics analysis, and this cylinder and this cubic, and we always use them to represent robot joints. Okay, so the robot manipulators, and what are manipulators? Later we will show some examples. So the robot manipulators mean the real robot you see and the hardware you can see directly, which is the mechanical structure. Okay, and the rigid bodies, which are the links, they are connected through joints. And how we're going to control the motion of robots? Actually, all these joints and links, they form a kinematic chain. Say, for example, here, if a robot, it has 3 joints, and one joint, if it is rotating, it's gonna control the motion of the next link, and then further it will form a kinematic chain. So later we're gonna show that. Okay. As most of the robots, they have two types of joints, which are, we already talked about it, which is revolute joint and prismatic joints. And what are the advantages or disadvantages of both? So the prismatic joints, they have higher resolution. And so, for example, here, this shows a prismatic joint. If we want to achieve a motion distance of d, and we can see that the prismatic joint, it can move exactly at this d. And the revolute joints result in kinematic and dynamic coupling. So for example, this is a revolute joint, it can achieve rotation directly. And if we count the distance from here to here, and that is d2. And from these two figures, we can see that the rotational link, which is the revolute joint, it needs smaller space to achieve this d, and this prismatic joint, it needs a larger space to achieve the small d. Okay, so also it's based on different motions, different desired motions and tasks, we may use different type of joints to achieve the manipulator design. And what is a robotic system? And we have seen the robotic systems in those examples in those YouTube videos. So what are the components in those robotic systems? Okay, and of course, and we should have a input device. It could be a touching pad or different things. So it gave the input. And also we need a controller, and which is a computer. for most of the real robotics, and we at least need a Raspberry Pi or a more functional, a high functional processor, so that we can install the ROS system and we can install the Linux system, and so that we have a computer in the robotics. And then we have sensors. And we have the robots, and the robots needs to talk to the surrounding or needs to talk to the human, so we need the sensors. And when we do the programming, and we need the program storage, and we also need the network, and sometimes it's like cloud control, and so we have the network. And here the controller is controlling the plant. In control system, we call it plant, but in robots, it's actually a robotic arm or a mechanical arm. And this thing is the manipulator, the mechanical structure. And of course, we need power supply, although we cannot see that in those examples, but there must be a power supply. And also here, at the end of the manipulator, we need to install some end of arm tooling. It's based on different functions. So for example, if we're a milling machine, we need to have a milling end of the arm. Okay, so that is a basic structure, the block diagram. So what are the end tooling? So for this part, what are those? So it is totally based on the tasks we need to achieve. And there could be a lot of different end effectors based on the functions we need. And basically, this is a wrist. This figure is a wrist for a robotic arm, and probably most of the common end effector, and that is a wrist, and a robotic hand. So here we can see that if we consider this part is the end tooling, and at the end of the manipulator, which is right here, and that is at this point, that is the wrist center point. And we need to exactly understand what is the motion of the center. And later we're going to show that we need to understand the coordinates, we need to calculate the coordinates, and based on the different input from the motors, the different motions, we can clearly understand the path of this wrist center, so that we can achieve different motions of the end effector. So this part, no matter what is the tooling, it is called end effector. And so for the spherical wrist, and so for example, this one, and for the spherical wrist, and it has all revolute joints. So for all revolute joints means in the total manipulator, there are 3 joints, and if they're all revolute, so we call it RRR. Later, we're going to show different type of manipulators. And they're intersecting at one center point, which is here. And the end effectors, and they're carrying tools, and they're capable of opening or closing or holding a cup. They can do a lot of things. Degrees of freedom. So the degree of freedom, this concept, it seems common. And so if we talk about rigid body, how many degrees of freedom do we have? We have 6, right? We have X, Y, and Z, and we also have the 3 angles, and around the rotation around the 3 axes. So for the robot, for the manipulators, we also talk about the degree of freedom so that we can understand the manipulator motion. So the manipulators with less than 6 degrees of freedom cannot achieve some points in the workspace with every orientation. And that is easy to understand. So why is that? So first of all, let's see what is a robot workspace. So here is a video shows.
The manipulator executes all possible motions. The shape of the workspace dictates the applications for which each design can be used. This demonstration lets you load several robot designs to compare their workspaces. You can set the position and range for each joint using sliders.
So we can.
This demonstration dictates that.
So we can see.
The manipulator executes all.
Okay, so from this example, that is a simulation of a simple robot manipulator that has 3 joints. So we can see that this is the workspace, and here this is a cylinder. So what is a cylinder? What is the joints of that? that is a revolute joint, right? And so from the joints we just saw in the robotics, we use cylinder for revolute joint, and here we use cubic for prismatic joint. Okay, so in this example, it shows that, okay, so in the simple manipulator, we have two revolute joints when we have one prismatic joint. And based on the different motion and rotation of these three joints, and the end here, the end effector, it can achieve the different spaces. It swipe in the robotic workspace where freedom, it's possible that it can swipe all the points in the workspace. Okay, so then it goes to the interesting figures. I want to show some interesting manipulators. You may see that before and in different scenarios for them in some videos, and you may see these orange ones, right? These orange ones, and that are pretty common in industrial robotics. For industrial manipulator, they have been used already in the industry, especially in manufacturing. And robots was born as combination of teleoperators and NC milling machines. That was the history. Okay, and these two manipulators. Okay, again, this whole hardware, these whole mechanical structure is called manipulator. And these two are two examples of typical industrial manipulators. And this one is from the company called Adapt6, and the thing is Adapt6 600 robot, which is here. Okay, and this part is the Adapt6 300 robot, and that is smaller. And both are 6-axis high-performance robots. And these two robots are designed for material handling or assembly, and they're used in manufacturing industry. This one is a RRR manipulator, and we call it articulated manipulator. So here we will start to talk about different types of manipulators. So this orange one, that is the ABB IRB 1400 robot. And from the video, we have seen those orange robotics and with different end effectors with different tooling in the end to achieve different manufacturing tasks. Okay, so what's that? If we want to understand it, if we want to understand this manipulator, we need to go into the details and see what is inside. So for this manipulator, if we take a look at the joints and links, again, because the robots are the combination of joints and links, if we want to do the analysis, first of all, we need to understand what are the joints and what are the links. So for this one, if we zoom in and take a look at those links and joints, so we can see that right here, there should be a revolute joint so that the whole manipulator can do the rotation around this axis, right? Around here. Okay, so that is the revolute joint. And right here, if we take a look at this part, and of course, here we have another revolute joint so that it can achieve the rotation. And right here, apparently there is another revolute joint so that we can achieve this type of rotation. Okay, so if we consider all the joints in this manipulator, so it's kind of straightforward. We have one revolute joint, second and third. So in this manipulator, we have 3 revolute joint in this manipulator. So that's why we call it RRR is short for one revolute, and one revolute. And if we want to do further analysis and calculation of the robotics, we need to extract the model. So the model for this manipulator, that is, here we have the cylinder, and the cylinder is a revolute joint, and here we have a revolute joint, another revolute joint, and here we have the third. And further, we will start to talk about these coordinates in the following lectures. So here shows that if we want to do the analysis of the whole manipulator, we need to define the coordinates. So we have here, we have the world coordinates in the base, so that we have the z0. And for every joint, that is actually a space, and we can define the xyz of this space and this space. And we also consider the rotation, so that finally we can do the analysis based on the mathematical modeling. And for this one, this thing is very common, this articulated manipulator, because it is similar to a human. Why is that? Because right here, we can assume that this is the body, and it can rotate. And right here, it's like over joint of our shoulder, that you can lift your arm, and right here, you have the elbow that is like your own elbow. You can lift it and you can rotate it, right? So here we have the 3 revolute joint, so that is similar to a human body, the human arm. Okay. Again, so the robot workspace, it means the total volume swept out by the end effector as the manipulator executes all the possible motions. Okay, so from the video we have seen that all the space swiped by the end effector, that thing, we can, if we cover those spaces, that is the workspace of the robot. Okay, and for manipulator, the manipulator geometry and mechanical structure, it define workspace. So what are the reachable workspace? And based on the further calculation, we will be able to see that. Okay, so for example, this 2 figures shows the side view and the top view of a workspace of a RRR, which is the RRR means the 3 revolute joints manipulator. So if we take a look at the side view, so here we have the base, and here we have one link, and we have revolute joint. So if we think about what are the space swiped by the end effector, so this is the space. Okay, and right here, and from the top view, we can see that these are the spaces that the robot can achieve. Okay, so another typical example of the RRR is this one. This is also from ABB company, and this is the ABB IRB 6400 manipulator. So it is use a parallelogram linkage. So if we take a look at the structure right here, and we have a parallelogram right here. Okay, so it has alternate revolute joint, and it has lightweight links, and it has smaller motors. So this is another version of the RRR manipulator. The next one. So if here we have seen a photo right here, and this is a pretty old manipulator, and this is a spherical manipulator. So, and this arm is called the Stanford arm. That is an example of a spherical manipulator. So if we go into the joints of this manipulator so that we can extract the model of the manipulator, and we can see right here we have a base, and so that we can achieve the rotation of the base in between the base and the robot, which is right here. And the second joint, which is right here, and that is a revolute joint, right? Because we can achieve the up and down, we can achieve this type of rotation. And also the third joint is a prismatic joint. So if we take a look at this part, and this inside can slide, right? Slide in this direction. So that is a translational motion. So that is a prismatic joint. So for this manipulator, one revolute joint and the second revolute joint and one prismatic joint. So we call this manipulator as RRP means revolute, and prismatic, which is right here. Okay. And the next one is Scara Manipulator. And if we take a look at this photo and let's do a quick analysis of the joints of this manipulator. So right here, apparently there is a revolute joint so that the whole thing, it can rotate, right? It can rotate like this way, this length, right? It can rotate. And right here, of course, there is another revolute joint so that the robot, it can do the rotation around this axis. And the last one, the last part is right here so that it can achieve the sliding, but it cannot rotate. So for this manipulator, again, this is R, and P, which is prismatic joint. And for the last manipulator, it can achieve the motion only in this direction. So for this manipulator, it is also called RRP because there are two revolute joints and one prismatic joint, but it's a little bit different from this spherical manipulator. So this is because for the Scara manipulator, the interesting thing is all the axes, 1, 2, 3, all these axes are parallel. Okay. So the next one, and this looks not that like a robotic arm, but it is a robotic manipulator. So again, we do a quick analysis. So right here, there is a revolute joint, so it can achieve the rotation between the base and the arms. And then right here, there is a prismatic joint so that we can achieve the motion, the translational motion. And then we have the translational motion around this axis, along this axis, so that we have the third joint that is prismatic. So then if we draw the model of this robotic manipulator, we have 1 R, P, and P. So that's why we call it RPP. Okay, the next one. This one is a little bit special. And for this one, it is actually larger if we want to achieve the same distance as a basic RRR. But the good thing is that it can achieve very accurate motion. It is because all the motions are achieved by prismatic joints. So we can see here we have the motion, and here we have the translational motion, and we have the translational motion. So then quickly we draw the model that is P, P, and P. So this is called Cartesian manipulator. So that is P, P, P. Okay. So if we compare the workspace, of different manipulators. So we take a look at the first one. If we have this model, what is the manipulator of that? RRP, right? If we use RRP, and this is going to be our workspace. Again, the workspace means the wiped space that the robotic can achieve. And this part is this one is RRP. But in this example, the prismatic joint, it has the translational motion along this axis. It's different from this one that is along this axis. And again, in this example, 1, 2, 3, these three axes of the three joints, they're parallel. Okay, so then if we consider all the spaces the robotic can achieve and the effector can achieve, so it means the whole space right here. Okay, and this example, that is, what is the manipulator of that? That is RPP. And for this one, it can swipe this whole area, this big. So that is the workspace for this manipulator. And the last one is PPP. And that is interesting because there's no rotation. So finally, the workspace it can achieve, that is a cubic. And we can accurately control the motion. But comparing to those three examples, we can see that the workspace is much smaller. Okay, so here I'm going to stop here for the first lecture of robots, that is the introduction to robotics. So next time, from the next lecture, I'm going to talk about the transformation. I will start to talk about the transformation, which is the basis to understand the workspace and these workspace and these modeling. So we need a world coordinates so that we understand every point in the whole in the whole space of the robotics, and we need to understand every point, the coordinates of those, and then we need to finally understand the end effector, the workspace of the end effector. Okay, so I will stop here for today, and today there's no quiz, but in the following lectures I may post some quizzes, and you will be able to find those on Canvas, and you will need to submit those quizzes. And this is just to motivate everybody to take a look at the lecture. Okay, thank you for your time.